Yes. Wow. I don't know how that happened. Thank you, Alinelli. And for a minute, I was going to be like, yes, I always do. You're right. It totally was not on. I'm so sorry. Okay. But, and I'll also distribute the notes. All right. Yikes. I totally did not realize that. All right. Okay. So I'm saying, so going back to this, I'm saying we're given this differential equation out of nowhere. We're not expected to know anything about K's or Q's or R's. We're just supposed to know that they're constants. Now we're being asked, is this expression, and I'll write it more neatly again in a second. We're being asked, is this a solution to this? This is the kind of question we were asked over and over in math methods too. Okay, it is a confusing question. We're saying like, it's like saying, here's a question, is the following choice answer to that question or not? Like, it's like a question within a question. So here's a differential equation. Does this expression work as a solution to that differential equation? What that really means, whenever anybody asks you that, what they're really saying is, take the expression being tested, take the function, not the differential equation, the function for x, take it and take its derivatives, differentiate it until you get the kind of derivative that the differential equation is talking about. Like our original differential equation is talking about the second derivative of x with respect to time. So take two derivatives of x with respect to time and see if we get something that resembles the right side. Like that's always what we're doing. That is what I'm going to do here. That's the question. If someone says, does this solve that differential equation? Is this a solution to that differential equation? They're asking, if you differentiate appropriately, do you get that original thing? Okay, wait, so I'm going to do that in a second, but there is a question. Sorry, please. Yes, Jenna, please. Yes, question.
So on the screen, it says, you circled the equation right there, and the KQ over R3 is square rooted. But in the test, in the expression that we're trying to figure out if it's a solution or not, it's not square rooted.
Oh, really good point. Wait, am I making mistakes all over? Wait, if that's true, that's really good. Hold on, let me look at the, if I'm miscopying something, then that is definitely important. Hold on a second. I mean, I will say this before I look. Great, I'm glad you're raising it, and that would explain why, if that's why you wanted to see this, that's a really good reason, and I'm glad we're going over. One thing I'm going to look in a second. No matter what, I do want to do the same. I have to do the same test. No matter what the thing says, I'm going to take two derivatives and see. But you're right. If I'm taking derivatives of the wrong thing, if I'm looking at the wrong expression, hold on a second, then that's bad. Oh, you're right. In the thing, it does not say square root. I'm sorry. Okay. That's a really good observation. Thinking that's like 1,000,000 points for participation. Now I totally do see why you wanted to see this, or why anybody wants to see this. So let me back up once. So I'm going to make a new neater. I'm going to add a page and make it more neat. To everybody. So no, she's totally catching an error in what's the error? Let me be as clear as I can. There is an error that Jenna just caught. And of course I'm embarrassed. I mean, but I'm very pleased that she caught it. What's the error? And so I'm going to try to do this cleanly here, but what's the error? It's not, so I don't want anybody to like suddenly panic. It's not an error in the question. And it's not an error in what I'm saying is the way to answer these questions. Like the way to answer these questions is you take the expression, you differentiate twice and see if you get the differential equation. But what Jen is pointing out is in my solution, I assumed I miscopied the expression that was being given. I basically thought of one that would work, but the one in the question does. She's totally right that the one in the question does not have a square root in it. So I'm going to right now freshly and I'll update the solutions. So thank you. So here we go. So we're given this. This is still what's given. That's what we're given, and now we're testing this. Now I put a square root in here. She's right. I thought we were testing something that had a square root in it just because I was already wanting the answer to work, but I shouldn't have done that. What the actual thing says is this, apparently. Okay, and stop me. So I think I got it right. So I'm going to test. So I will change this in the solution to the exam. Again, I'm not trying to beat a dead horse, but right, I tested the wrong thing. I miscopied in the solution. I miscopied what they were proposing as the, so we're going to take derivatives here. Oh, okay. These are all good questions. Okay, hold on. One, and let me make sure I didn't miscopy again. Oh, okay. Okay. So I'm seeing questions in the chat. So I'm just trying to do this and address the questions in the chat. Let me, okay, a couple of things. Let me, and again, there are good questions in the chat. And again, I guess this is why we practice, right? Oh, I mean, I'm really pleased that someone asked, that someone was pressing on this first question, but all right. So first of all, this is what I think the correct way to do it is. I hope you'll see it, and I will, well, I'm going to share these lecture notes anyway, but I'm going to post an updated, corrected version of the exam. Corrected version of the solutions. I would do that anyway once I have the solution to the third problem. So, you always want to look out for the updates and take the most recent version no matter what. But this is definitely a correction now. I'm now saying, even though I'm following the exact same procedure that I followed when I tried to solve this on paper for very first question of the exam, I'm following the same procedure, which means taking the given expression and differentiating it twice and seeing what happens. Only here I've taken the actual expression that they actually gave me in the problem, and I'm making that and I'm taking two derivatives. I want to address that in a second. I'm taking two derivatives. And then getting to that final step and realizing, aha, all this thing here was the original x that was being conjectured. So I can substitute all that with the term x. And now I look and I have something to compare to the original differential equation. Like I now have a differential equation. The question is it the original? And now I say no, because that KQ over R cubed thing came out twice. So it got squared, like there was no square root to compensate. So no, I'm ending up getting I'm getting a square of the original constant, not the original constant. So now my answer is no. But one other question that was in the chat is what happened, I think, if I'm understanding the question, is what happened, like what do you do with this pi over 2 business, or why is it there? What's the purpose? Well, the purpose of the pi over 2 is that it does get carried along for the ride when you take derivatives, but it doesn't go away when you take derivatives, but it also doesn't come out and act as a multiplier the way KQR cubed does. Why? Because we're doing chain rule. So what we're really doing each time we take derivative, we're like when we look at this original expression, we're using chain rule. We're viewing this expression as a function of a function. This is cosine of something. What's the something? The something is constant times t plus constant. Like, so we have to take the derivative of what's inside this whole thing. And the derivative of what's inside this whole thing gets multiplied by our other derivative, by our outer derivative. So what's the derivative of this whole of this entire inner expression here? The derivative of this whole thing with respect to t, the derivative of it is simply kq over r squared, because the derivative, because pi over 2 is a constant, and the derivative of a constant is 0. I don't know if I'm making any sense, but so when we differentiate this inner quantity, the derivative of it is literally just the constant next to the t. It's just kq over r cubed. That's the derivative of the whole. Technically, it's that plus 0. It's the derivative of the constant t term plus the derivative of the pi over 2 term. So it's kq over r cubed plus 0, but plus 0 means plus 0. So what comes out is just a kq over r cubed. I don't know if that's addressing, but yeah, the pi over 2, nothing happens to the pi over 2 when we differentiate because it's a constant. I don't know if I'm really answering that question or not, but okay. Oh, right, okay, good. So the pi over 2 doesn't come out in the derivative. In the first derivative, only that kq over r cubed comes out. But now we take derivative again. When we take the second derivative, we do literally the exact same thing again. So we're doing chain rule again. We're taking the derivative of the whole thing, like whole thing meaning, oh, we've got a negative cosine here of something. So the derivative of that is negative. I'm sorry, we have, derivative of we're taking derivative of the whole thing. So we first have derivative of negative sine. The derivative of that is negative cosine. But now we have to multiply that by the derivative of what's inside. And we still have a kq over r cubed inside. Now we already have one outside we brought it outside from the first derivative. So we already now have one outside, but we still have one inside because the function still looks that way. So we bring it out again, like this is chain rule again. So we bring out that constant again to the outside. So it's like the second version of the constant being multiplied by the first version of the constant. That's why we get it squared on the outside, literally because we did the derivative twice. That's where the squared comes from. And that's why, well, I don't know if that answers, wait. Oh, yeah. Right, and the derivative of a constant is 0 because the slope of a horizontal line is 0. That is definitely true as well. So the reason I'm pleased with these, and again, I understand, like, okay, cool. Right, exactly. And since it got, right, so it gets squared, so the constant here, when I say the constant right before the t does definitely get squared entirely because we took 2 derivatives. That is definitely not a coincidence. That's the deal. So it gets squared because we took 2 derivatives, but because it got squared, then that became too large for the original presentation. So therefore it doesn't match the original differential equation. That's right. And that's why I stupidly square rooted in advance, because like psychologically, I wanted it to match because I forgot this is like a true false question. So, but yes, no, that's I'm saying yes to anybody in the private chat right now. And a couple people are asking, but yes. So yes, since it's squared, it does not match the original. So it is not a solution. And And that's the way this goes. So I don't know, hopefully if that helped anybody, I think maybe it helped me. So maybe I'll do, so the answer to the first part of the exam, the very first part of the first part is no, not a solution. Excuse me. And I should say, exactly, it's not a solution because nobody bothered to put a square root inside that cosine thing. If they had, it would have been. In other words, the pi over 2 didn't mess us up. The pi over 2 could have worked, but it was not putting a square root. Technically, those constants didn't have the right units, is why I didn't. All right, so I'm going to go now. Now that was, let me just see the time. Okay, so we have a little time. Now look, this is good. I'm going to keep going a little bit. I just want to make sure I want there to be a difference between preparing, reviewing an exam and going over exam solutions versus just me teaching. Like there should be, and it feels like there is a difference right now, thanks to these questions. Like one thing I'm trying to clarify with this, it's also good that you're catching my errors before they become total disasters. So that's good. But one thing that's very exam-y about this problem, hopefully you guys can see, in some ways, this is just the same. It's another exercise in the same thing that we're doing over and over in class, trying to learn, which is taking derivatives to see if a solution works in a differential equation. But so it's like the same thing. Hopefully you're seeing that you're getting more practice, more confident at it. But once you get enough confident at it, then we throw like weird looking constants in. Like the whole idea of this is to get us so that we're flexible enough that we can spot a differential equation and know what to do with it, even when we don't recognize its parts. Like it's deliberate. It is part of the test. I know you guys don't recognize Q over R cubed. That looks like it's just like you weren't expecting temperature to be mentioned on that homework. Well, I don't know what you were expecting, but like it didn't seem like we were talking about temperature, and it doesn't seem like this is a thermal class or a chemistry class, right? So like temperature just suddenly comes out of nowhere on that homework. Why? Because we're trying to reinforce that what's underlying is the harmonic oscillating differential equation. As physicists, we want to see that underlying theme and be able to apply it even in all these fresh circumstances. So the fresh circumstance of this exam problem is that the constants are now about R cubed and KQ, and they're supposed to not throw us. We could still do it. Now I want to tell you that KQ over R cubed, I'm not just putting things together just to be obnoxious and just to come up with some different combination. Like the truth is that's physics. You're going to see like nothing in here is just to be it's all physics. That is a different harmonic oscillator that we're going to see soon that has to do with a sphere, whether it's a sphere of mass or a sphere of charge. Like that's a real thing. I mean, it happens to be a sphere of charge because it's Q, but like everything in this test is a real thing from somewhere. And we're trying to hone our skills as physicists of being able to recognize physics when we see it as something similar to something we've seen before. So anyway, that's that exercise. I'll do one more. I'll do the next one just to, well, wait, should I? Well, wait, let me see. I would like to keep talking about this review test. I don't have another agenda, but if someone maybe has I guess I could just go on to the next one. But if someone would rather ask me something specific, I'll address that. Well, maybe, yeah, I'll just do one more in order just so we can keep, I'll do the next one. Oh, okay. Right, so we just did that. So I'll change it. All right. Oh, so now we get to B. In now the next, like B and C, very, very similar to A, very similar, like taking derivatives C, but we're just making a slightly, now we're saying, okay, now we're not asking whether these things match the particular harmonic. I'm sorry. In A, we present a differential equation and we said, here's a possible solution. Tell us whether it is or is not actually a solution. Okay. Now in B, we're saying, here's a possible solution. Here's an expression. You tell us whether that expression is or is not a harmonic oscillator. What that really means is you're going to tell us whether or not it meets the second order differential equation for harmonic oscillation in general. It's like now up to you to get what that means. And remember, it doesn't necessarily have to be a harmonic oscillator with a particular constant or a particular phase or particular anything, just as long as you can show that this expression meets the conditions of a harmonic, as long as you can show that this expression, when differentiated twice, does produce the differential equation that is harmonic oscillation, then you've done your job, right? So that's what we're going to do here. So like before, I'm going to take two derivatives and see what happens. Like here's in brown the expression that I'm testing. So now I'm going to, like it is a harmonic oscillator if upon taking two derivatives, I get back itself times a positive constant times a negative sign, which is really a way of saying times a net, right? If it does that, then it is a harmonic oscillator. So let's see. Okay, so let's see. Here's x. So I take the first derivative with respect to time, and I do just like I was talking with a minute ago, I do chain rule. So that means first I say the derivative of cosine of anything is negative sine, but then what's inside the derivative of it. Oh, did I recopy it? Oh, hopefully, did I copy the expression correctly this time? I hope. Oh God, I'm worried I didn't copy. Did I miscopy the expression again? Hold on a second. Well, I'm going to assume I did. Excuse me. So here's the expression. I'm going to take a derivative. Yeah, and I do chain rule. Chain rule means I bring the constant on the outside, the square rooted constant, which I hope I copied correctly. And the derivative of pi over 2 is 0 because, like Yaverbaum said, because the slope of a horizontal line is 0. So here's one derivative right here. Then I take the derivative again now. And this kind of, okay, so I'm just trying to be careful here. Oh, sorry, is that a question? Go, Jenna, sorry.
So for question B, there's not a square root again on the paper.
Yeah, no,
so does that mean the result's kind of going to be like a no at the very end of the day?
Yeah. Did I do that again? Well, you're totally right to be pointing this out. I can't. Why did I do that? No, you are totally right. If I never put so now I'm starting to say that I want to put a square root in that original question because this is right. It's starting to just like waste time. If let me just go back. Hold on a second. No, you're absolutely right. If there's no square root there, there's no chance. There's no chance. God, how did I do that? Yeah, okay, so to everybody, it's true. I can keep churning through all of these derivatives, but you can see the pattern. If there's never a, oh, wait. Oh, no, wait, whoa. Sorry, hold on. No, we're still good. I'm sorry. This is okay. Everything that happened in the first part where I made an error and everything, yep, like there was an error. We've corrected it now, yep. Now, I thought I was losing my mind for a second. And I'm still think that what Jen is asking is a great question. But here's exactly, but we're still okay. There's actually not an error. This is all a worthwhile discussion. And we're not going to say no. We are going to find yes here, and I'll say to everybody why before I lose my mind completely. Although I still, let me say again, like thousands of participation points to Jenna, definitely, like, and anybody else who's following what she's saying and stuff, like this is a very reasonable concern. This is why it's an exam and why there's practice. It is true. There's no square root here anywhere on the page. And I'm not of the test. That is true. But for B and C, that's not going to cause an error. That's not going to be an error necessarily. Because remember, we just have to prove that this thing is a harmonic oscillator, not a particular one. In other words, and this is not meant, I mean, right, I'm falling into my own trap. It's not meant to be a trap, but if you look, the difference between question A and question B is question A, they're giving you a differential equation, and then they're giving you a possible solution to it and saying, does it work, yes or no? Does this key actually unlock that lock? And in question A, and thanks to Jenna's close, careful reading, the answer is no, it does not. Even though it comes close, it does not. Because up there, we want the constant of proportionality to be KQ over R cubed, which would have to mean that the square root of that appeared in our cosine expression, but it didn't. So our cosine expression does not solve that. So like in A, the answer is no, and it is because of that like lack of square root thing that Jenna said. But now in B, we're just giving ourselves an expression and saying, could this thing be a harmonic oscillator? Could it, when differentiated twice, yield d2x dt squared equals negative omega squared x? Like, could it satisfy that? And the answer is sure. I mean, we'll see in a minute, but I want to say, oh yeah, it could, because no one's telling me what that omega squared has to be now. Like now we're just saying as long as when you differentiate this thing twice, you get itself times a constant. Like again, even if there's errors going, a constant, not a particular constant, but any constant, as long as it is a constant times x times a negative sign, then we're good and it's a harmonic oscillator, maybe with an angular frequency that we didn't expect, but it's a harmonic oscillator. And I'll bet you, I'm sure I still forgot about the square roots and everything as I did the solution, but I do want to say that clearly to everybody right now, like we're going to do this, and it's probably where we'll end today. Oh, maybe not, I don't know. But I'm going to take the derivatives and everything, and maybe I'll even do a blank paper now so I don't even look at the posted solutions. But our goal now is just to see if we get a harmonic oscillator, not necessarily a specific one. And in fact, like, and that is why question B is different from A. So I'm going to slowly and carefully do this on a fresh sheet of paper. I'm going to do this now. So I'm not as, but again, this is all still saying that I think the question's super important, but it's also super nuanced. So here I go. So B, I'm going to do it fresh. Hold on a second. Wait, am I even look now? I'm really confused with myself. I lost it. Wait, no, and if we skipped something, then maybe I didn't mean to. Maybe I'm really losing my mind. Hold on, let me get, I think the problem is I don't have the sheet pulled up properly. Hold on 1 second. Something is definitely happening. If we skipped something, like yeah, well, hold on. Okay, I am intentionally right now, and I apologize again. I'm just looking at the questions right now, seeing what we skipped. Okay, we did 1. Oh, no, God. No, first of all, I skipped A. Okay, A sub 2, I skipped for no good reason. I just skipped it right now. Like, and I don't want to confuse things by going back to it right now. But in theory, I'm just answering random questions here today anyway. So there's no good reason that I skipped A2. We could talk about that in a second. And obviously, I'm going to go back when this is all over and check my solutions and see how deeply this error permeated everything. But right now, I feel that we have correctly answered A1 as a class today, right now. A2, I skipped right now for no reason. I could just tell you the answer though. Hold on. Right, that is going to have the same. I do agree with Jenna and possibly anybody else that A2 will have the same problem that A1. Like we should get that the answer is not a solution. It should not work because that KQ over R cube thing is going to get squared and it won't work. Like, so the answer for A2 will also be no, whether I skipped it or not. I don't know if that helps. Now, B, I'm going to B now. And I want to say with B, I'm looking for the right page to do it, but B is more subtle. B, it's, because B, yeah, here we go. Okay, B. I'm just going to do it fresh right now. Okay, so now we are just trying to show whether this is or is not harmonic oscillator. Okay, so in my mind, that means does is this true? Okay, but remember, omega squared is any constant, right? Like omega squared could be any group of KQ over R cubed. It could be the square root of them or squared. Like it could be whatever we want it to be, right? We haven't, whereas in problem 1, it was specified to be KQ over R cubed. Okay, so that bearing that in mind, I'm going to take derivatives, maybe quickly. So that's my first derivative, right? I'm losing. Sorry. Oh, chat. Let me just make sure. Yeah, I skip. Yeah, sorry. Yeah, right. I am sort of skipping. Right. That is true. Okay. So I have this is first derivative, and now and remember one thing, and I'm also trying to emphasize with sneaking this little I business in. Like the one main thing to know about I. Well, sure, it's the square root of -1. That's actually all you need to know about it. But really, even better than that, just knowing that it's a constant. The I is a constant, even if it looked right. Just and so is pi. So I take the second derivative. Now, what comes out again, the only thing that comes out, so to speak, from chain rule is that KQR R cubed thing. Like that comes out again, that gets squared. Notice, and this is a little tricky, like I does not get squared here. Like the KQ business is going to get squared, but not the I. In other words, I'm saying this. Okay. So the I does not get squared. We have this. So now we have apparently right. So I'm going to pause here. Maybe I don't think I made a mistake this time. And I think this is worth pausing on now. So and I know we're skipping things, but this is now part 1B, 1 and 2. Do you think the answer is yes? Like this is tricky, but is the answer yes or no here? Like, is this expression, this I cosine blah blah, is this? And I don't even look at my solutions that I posted. I'm not even saying whether, but just looking at what we just did right now, looking at it fresh as a class. Does this thing work or not? Is this thing a harmonic oscillator or not? Yeah, okay, I just got, sorry, just because, yeah, I just got a private check. Sorry. Awesome. Yeah. Oh, sorry. Sorry. Okay, to not have it because this is exam and I want to keep the answer is yes. Like I just got a couple of things in the private chat. I'm very pleased and proud. Like people are, and I know that I would go in the private chat too right now. Like I would feel trepidatious. So this is all a little bit confusing and it's never good when there's an error, of course. But the answer is yes. I got a couple answers in the private chat that were yes, and those answers are correct, and they're very correct. And I'm very pleased. Let me like I'll take one more page. Hold on a second to be as clear as possible. Like this is what we have so far, or what we just wrote. We wrote this. Oh, sorry. I know there's a squared. Sorry, that's not true. Yeah. Sorry. Okay, to make things as I'm almost glad. I'm not glad I made a mistake. Obviously, that's not. But the fact that we're grinding down on these like really nuanced, tiny difficulties of this could not, in a way, be a more perfect thing to do now, like a couple of weeks before the actual exam, because this is. I mean, if you can follow all this, then you definitely get why this is a question in the first place. Is blah a solution to the differential equation blah? Like it does take some thinking, right? But what I'm saying here, and I'm agreeing with the 2 people or 3 people in the private chat, that definitely the answer is yes here, but notice the subtlety. Like the reason the answer is yes, the reason that we're saying x equals I cosine blah, 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 is a harmonic oscillator is that because whether we did get this, we got the thing written in red. We ultimately got that when you differentiate it twice, you get a second derivative equals negative blah, 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 squared times x. That's what we got. But I want to say, like, even if, and I know that that squared is there. Like, that's what actually annoyed us in problem 1, that the squared was there. And problem 1 didn't want the squared to be there. But the squared can be here for part B here. Like, if that square is there, I'm saying the answer is yes. If that square, sorry, my whole point. This would have been true. I'm saying this too, down here in blue. This is not what we got. But I'm saying if we had gotten that, that also would be a harmonic oscillator. Actually, if we had gotten cubed here, it would be a harmonic oscillator. Actually, if we had gotten 1/2, or in other words, this whole thing could have been square rooted and it would still be a harmonic oscillator. The point is that it's a harmonic oscillator if the second time derivative equals negative times a constant of any constant times the variable itself, x, right? Whatever this constant is, its square root will be angular frequency. So one angular frequency is one harmonic oscillator and a different angular frequency is a differently rated, is a faster or slower harmonic oscillator. But it's a harmonic oscillator as long as it has an angular frequency at all. This one does, even with that. Am I making any? I don't know. So I'm saying, yeah. Oh, okay. Right. That's what I'm saying. Yes. I'm just going to read this out loud. I'm not going to say anything, but someone just put in the chat, in the private chat. This question wasn't asking about a specific solution, but just whether it is a simple harmonic oscillator or not. So the square root doesn't make too much of a difference. That is entirely what I'm saying. I'm saying here we shouldn't get thrown off by that square root. It's okay as long as we're as long as we're understanding, we're just trying to prove that this is a oscillator, not a particular one. That's right. So the answer is yes to this one. I think we find, by the way, that the answer will also be yes in the next one with sine, it turns out, for what, because the same thing happens. But right, we're going to pause there for a second. Just let this, so you may just look over and make sure you're clear at whatever level on those, like everybody. Let's just pause on that for a second and I'll collect my thoughts as well. Okay. Again, let that, I'm glad, we still have time Wednesday to talk about this stuff too, but really make sure, oh, okay. Hold on a second. Oh, good. Well, I'm glad to hear that. Thank you. And I'm sorry. Good. Thank you, Alyssa, for saying that. I'm glad to hear that. But now I'm also looking at something in the private chat. Yes, that's a very fair thing. So clearly I'm going to have to correct. Obviously, I'm going to have to update my solutions and correct. Because yes, let me look at the period thing. That will be affected. Hold on. Let me see where that comes up. Oh yeah, okay. So I'll do that very quickly right now. Yeah, because that may well be, if I drop the square root accidentally in the posted solutions, then that could be an issue. So I'll do one more step of this to show the period. Right. Oh, right. So it asks, is this harmonic? I'm still on part B. Part one is, does it satisfy the differential equation for harmonic oscillation? I say, yes, it does. And then two, really, and I'm glad someone is asking me about this in the chat. Part sub 2 of B is, if so, determine the period. Now that's a good way of saying, like, it's not only show me the money, partly it's like show me the money. Like, well, if you're saying it's a harmonic oscillator, you're saying that it swings back and forth at some steady rate. Like, to say it's harmonic is to say that the rate is steady. So this is kind of like saying, well, if you're going to assert that this system is oscillating at a steady rate, then you should be able to tell me what the rate is. Like, that'll satisfy me. That'll prove that it's going. So in effect, that's what we're doing. And we're assuming that period is inextricably linked to frequency, which is inextricably linked to angular frequency. So I'm just going to solve for the period. But Jenna and others are absolutely right that in order to solve it, I better make sure I have the angular frequency right, which means I better not be careless with the square roots. So just in case, so this is problem one, part B, subpart B2. Okay, this is the way I always think of it. They want period. We want the amount of seconds per one cycle. I say by definition that is the reciprocal of standard frequency, the number of cycles per 1 second, right? Now, where do I get that? Well, that's just angular frequency, but bearing in mind that angular frequency measures in radians per second rather than cycles per second, and bearing in mind always that there's 2 pi radians for every cycle, right? In honor of Pi Day yesterday, yay. So I'm gonna take my omega, divide by 2 pi, and then flip that to get my period. Now here's where I have to be careful. According to this thing, and I may have messed this up in the post solutions, but according to this thing, here, according to this, omega necessarily is KQ over R cubed. Not square root of that, but just that, because that is what is appearing right before the T independent variable term in the cosine argument. Put another way, like T is measured in seconds, so whatever constant is represented by the parenthesis next to the T, that must be a constant that is measuring in radians per second, whatever it is, right? So that constant next to T is omega. It just is omega. So if that's omega, sorry. And yeah, the more I'm looking at this, I bet I did screw this up in the solutions, but this would be the answer, and I'm sure I'm off by a square root thing but that would be the answer to problem 1, part B, subpart 2, if that makes sense. I'm gonna look in the chat again, sorry. And again, if this differs at all with the posted solutions, that's because I missed that square root thing. I will just, and I'm just gonna clean those up quietly in my own time, and then just I'll repost updated corrected solutions so that in a clean copy, so you don't have to keep flipping it. Okay, but I'll do that later. So this is what I'm saying the answer is right now. And I know it's 120. Is that cool? Okay. Maybe I think the best thing for me to do, given that we have 10 minutes, I think, let me give you an overall, well, let me think for a second. Yeah, let me just talk to you in an overall terms for a moment or two about the next problem 2, whether you've looked at it or not. Okay, I hope there's no errors in my solutions there. So hopefully if I can give you an overall comment, my solutions may be of some help. And again, we can keep talking about this Wednesday, but Okay. Oh, chat. 1 second. I know. I'm alone. Okay, sorry. So the first note I want to make about this pendulum thing, like also, you know, the problems, everything in this exam is all about harmonic oscillation, but it's kind of amazing how much, you know, how much there could be to say about that, right? Like, but so, and the problems are getting sort of progressively, I don't know what. The second problem is meant to relate to stuff in your lab, but the first thing I have to say about it is you're told this weird twist that the whole problem is being done way underground. That's not supposed to throw you off. It's not supposed to make you do the problem differently or suddenly panic. But it is a typical physics thing where there's like always some twist or some new blah, blah, blah. And the blah, blah, blah here is that you're way underground, which simply means I'm telling you, and we're going to actually find out in problem 3, weirdly enough, I'm telling you that if we're way, way underground, that one assumption you want to throw out the window is that G necessarily equals 9.8 meters per second squared. I'm not telling you like why, or I'm not telling you what it does equal. And I'm not even telling you that you need to use what it equals, right? So it's not, but I am saying whatever we've believed about 9.8, like that's kind of true on the surface of the Earth. It's not true everywhere in the universe. It's not true in the inner core of the Earth. And so I just want you to unlock yourself from any attachment to that number when you do this problem. Why would I even say that? Like, is that just to, I mean, that might stress, why am I even bringing that up? Like, who cares? I'll tell you why. And I know we have 5 minutes. Because this problem is, the second problem in the exam is meant to turn your harmonic oscillation attention back to where you've seen it in the lab, like to show you that it's not just masses on springs, it's also pendulums, and you've seen those in the lab. And therefore, I know that there's something you might know from lab. Okay, this is what I want to be careful about. Like, sorry. Okay, and now I see, I know we have 4 minutes, so let me be very careful about this. The reason gravity is coming up is that something you might have picked up from lab or something that you're in a way going to show here, something that you, as much as you understand period and frequency with masses on springs, hopefully you've extended that understanding and you've seen in lab that period and frequency also applies. It applies to all oscillators, including pendulums. And the way period works in the pendulum is that it's not related to square root of m over k, it's related to square root of L over G. I'm not saying you're supposed to memorize that, but I am assuming that you kind of know that at this point. I'm saying 2 things about it. One, you're actually going to really show that in this problem more than using it, you're going to show it. But whether you use it or show it, I just want to emphasize that what this means G. Like it means G, even if you assume this expression. The truth is you shouldn't assume it doing problem 2. You're really going to end up showing that it's true. But even if you assume that you know how period works in a pendulum, be very careful. Like when I ask you questions at the beginning, when I'm asking questions about angular frequency at the beginning, don't just assume that you know what the period is and then flip that or something, because you don't like, because I get I'm saying this all backwards. What I'm really trying to say is one of the ways that we actually know what G is, one of the ways actually to learn what that G is 9.8, one of the more straightforward, simple ways to find out or prove to yourself is to use a pendulum, is to measure the period of a pendulum and backwards infer and know that since it must be 2 pi square root of L over G, that if we know the T, if we get the period, then we can multiply both sides or we square both sides and we can get G from that. I'm saying I'm really trying to say, when I ask you for frequency or period in this problem of part 2, don't use G to get them, because because G is not 9.8. You don't know G. That's really what we're trying to figure out in this problem. So what I'm really trying to say is stick with the differential equation as we're practicing. And I don't think I made an error in these solutions. You'll see in the solution, but I'm really trying to say that if the problem starts off by telling you, if the problem says something like this, I think that's what it is, right? Like, you know, those thetas could have been Z's or they could have been X's. I want you to recognize, oh, this is the differential equation for harmonic oscillation. That automatically means that we've got theta oscillating at an angular frequency, like angular frequency is like, this is always, I mean, this is just, in other words, like homework 3, the heat homework, we're just trying to drum into our brains that harmonic oscillators exists everywhere. And you want to be able to recognize them even when they're sort of disguised, right? And the X could be disguised as a theta, or the omega could be disguised as a number, or blah, blah, blah. But if you see that this is the second order differential equation for harmonic oscillation, and you see that that thing in the parentheses is the constant proportionality, then that must mean that the omega for this sucker is the square root of that constant. Like, this is an oscillate. It must mean that this thing is oscillating at an angular frequency of pi over 4 radians per second. Like, that's how the problem proceeds. Like, that's the first thing you want to take away in part A or part B of this problem. Don't try to get the frequency by using 9.8. Because we're telling you, you don't know that it's 9.8 because it isn't, because we're deep underground. And if you then say, wait, I didn't know that gravity changed deep underground. Am I supposed to know that? We're going to say, no, you didn't know that. We're just saying you never knew anything about 9.8 other than it was true at the surface. Like we're not saying you need to know it. In fact, that's where this course is going. We're going to show you in the next problem why gravity changes when you're underground. But for now, we're just saying, since you don't know what gravity is doing, don't rely on the G number. Rely on differential equations to get this answer. Okay, it's 1:30. Sorry, I've talked way too much. We'll keep talking about this Wednesday. I'll update the solutions. I'm so sorry. I will wait for 2 minutes for goodbyes or for questions. So most of this was recorded. Sorry, the beginning wasn't, but I think all the meat was. I will post it. So I'm saying goodbye if and when you guys. Thank you, Sharon. All right.
Have a good day, Professor.
You too. Thank you very much.
Have a good day.
Bye, Professor. Thank you.
Thank you very much. Awesome. Thank you. Thank you, Andre. Thank you, Sharon. Thank you, Jenna. Thank you very much, Jenna. Thank you, Justin. Thank you. Awesome. Thank you. Awesome. Thank you, Andre. Okay, Heaven, Justin, Jumbo. You guys are good. And I actually do have to hop off and go get if we're good. Or are there questions? Are we good? Oh, okay, we're good. Cool. Thank you. You guys are good. Heaven and Yabo, you're good. So if not, I'm gonna go. I think if that's okay, I'm going. I have to go pick up my. Thank you guys very much. Great. Good to see you. You're the best.